Hi everyone. In this example, I will explain you how to sketch the root locus for a given system that you can see here. So as you can see here, we have the controller GC of S as KP. It's a proportional controller. Then GP of S in the form of S plus B or S squared times S plus A, for which B is always equal to 1 and A can take three values, 10, 9, and 8. So I will call them maybe GP1 as S plus 1 over S squared times S plus 10, GP2 as S plus 1 over S squared times S plus 9, and GP3 as S plus 1 over S squared times S plus 8. But in general, GP is equal to S plus 1 over S squared times S plus A. So as a result, our loop transfer function L of S, which is equal to GC, the controller, times GP, is in the form of KP times S plus 1 over S squared times S plus A. And if you want to use the row, then KP could be replaced by row S plus 1 S squared times S plus A will be our L of S. And we know that rho is equal to Kp. So now our aim is to draw the root locus for this system for three values of A equal to 10, 9, and 8. And we will see that based on the value of A, which is the location of one of the poles of the system, the root locus sketch will be quite different. So let's start as usual, determining the value for n and m. N is equal to 3 because we have 3 poles, 2 at 0, 1 at minus A, M is equal to 1, 1, 0 at minus 1, and as a result R, which is N minus M, is equal to 3 minus 1 or 2. So R is equal to 2. This means that there are 2 asymptotes for our root locus. Since we have asymptotes, we can start to find out how the asymptotes behave. And we need two parameters in it. One, which is xa, and it's the point of abscissa, or the point on the real axis where the asymptotes meet each other. And if you remember, it could be obtained as sum of zi's minus sum of pi's over r. We have 1, 0. So yeah, this is our L of S. Z1 is equal to 1 here. So we have 1 minus, we have 3 poles. P1 is equal to 0, P2 is equal to 0, and P3 is equal to A. So 1 minus A over R, which is 2. From here we have XA equal to 1 minus A over 2. So depending on the value of A, the point of abscissa will be different. And we also need to determine the angle for the asymptotes, R times KCA, which is 2h plus 1 times pi for positive locus, and 2h pi for negative locus. In the negative locus, rho is smaller than 0, and in positive locus, rho is bigger than 0. Since we have two asymptotes, we need to set h equal to 0 and 1. Therefore, we will have, setting h equal to 0, we will get pi. H equal to 1, we will get 3 pi for the positive locus. And h equal to 0 will give us 0. H equal to 1 will give us 2 pi for the negative locus. And now we can say that KCA is equal to these values over r, where r is equal to 2. So we will have pi over 2, 3 pi over 2, 0 and pi as the angles of the asymptotes for the positive locus and negative locus. All right, so we are done with the asymptotes. And now we can think about the parts of the real axis which belongs to the root locus. So this is parts or sections of real axis belonging to PL or NL, positive locus or negative locus. So this is what we have in general, with two poles at the origin, 1, 0 at -1, and one pole at -a. So this is real axis and the imaginary axis in the S-plane. So we can say that for the regions from -infinity till -a, we have 1, 2, 3, 4. 4 poles and zeros are on the right hand side of the test point. So 4 is an even number, and as a result, this section belongs to the negative locus. Then from -a till -1, we have 2 poles at origin and 1, 0 at -1. So we have 3 poles and zeros. Zeros on the right hand side of any test point. And 3 is an odd number, so this belongs to the positive locus. From -a until 0, we have only 2 poles on the right hand side of the test point. 2 is an even number, so this section belongs to the negative locus. And then from 0 till +infinity, we have 0 number of poles and zeros. And since it's not an odd number, or we just consider it as an even number, we can say that it belongs to the negative locus. So in conclusion, we can say that areas from -infinity till -a and from -1 till +infinity belong to our negative locus, and only from -a till -1 belongs to our positive locus. So this is our conclusion in terms of the segments or sections of the real axis belonging to our root locus. As the next step, we can think about the break-in or breakaway points. And in this section will be the most important part for this example, because depending on the value of the a, we will see that we may have a different number of break-in or breakaway points in each case. So I hope you remember how to find out the break-in or breakaway point, but I will start from scratch. So we have 1 plus rho n over d equal to 0, or in other terms, rho is equal to minus d of s over n of s. In order to find the break-in or breakaway points, which are the local maxima or local minima for the value of rho where s is a real number, we need to find out d rho over ds and set its value equal to 0 and find out whether this equation has some real roots. So finding d rho over ds, we will have minus d prime n minus m prime d over n squared. And if you want to set it to 0, we will have just m prime d minus d prime n equal to 0. Here we have n of s given as s plus 1. As a result, m prime is equal to 1. D of s is given as s squared times s plus a, and therefore d prime of s is equal to 3 times s squared plus 2a times s. And from here, now we can form this equality. M prime is 1 times d, which is s squared times s plus a, minus d prime, which is 3s squared plus 2as, times n, which is s plus 1 equal to 0. So we can just simplify it. We will have, here we have s squared times s plus a. I just rewrite it. Minus, I factor s out, so I will have s times 3s plus 2a times s plus 1 equal to 0. And from here we see that we have s equal to 0 as one of the roots. So s times s plus a minus 3s plus 2a times s plus 1 equal to 0. Therefore, s equal to 0 is one of the break-in or breakaway points. We will go into the details of this point, whether it belongs to the positive locus or negative locus. And then the rest that we have here should be equal to 0 to find out the other roots. We will have s squared plus a times s minus, so multiplication of these will provide us 3s squared plus 3s plus 2as plus 2a equal to 0. And from here we will have s squared minus 3s squared. So these terms will appear here, plus a plus 3 plus 2a times s. So these terms appear here. Indeed, here we need to have minus signs. Yeah. So here we will have a minus 3 minus 2a times s, and then we will have minus 2a equal to 0. So rewriting it again, we will have minus 2s squared. From here we will have minus 3 plus a times s minus 2a equal to 0. And we can again rewrite it in order to find the roots maybe a little bit more easier. So we will have, if we multiply both sides by a negative sign, we will have 2s squared plus 3 plus a times s plus 2a equal to 0. And now we need to find the roots of this polynomial. It will have two poles, s1 and 2, which could be obtained as minus 3 plus a plus minus square root of b squared minus 4 times a times c over 2 times a. So we will have what you can see here. Which could be rewritten as minus 3 plus a over 4 plus minus. So it's square root of 3 plus a squared minus 4 times minus 16a. So now the important part here is this square root. So if the term inside the square root is positive, or if it's equal to 0, or if it is bigger than 0, we will have 3 different cases. So I can rewrite it here. 3 plus a squared minus 16a could be rewritten as, so we have 9 plus 6a plus a squared minus 16a, or we will have a squared minus 10a plus 9. So in case this is equal to 0 for any value of a, we will have S1 and S2 equal to each other. In case this is bigger than 0, we will have two distinct S1 and S2. And in case it's smaller than 0, we will not have any real valued roots for this equation here. So let's see, when do we have s squared minus 10a plus 9 equal to 0. We can rewrite it in this format. I think it's equal to a minus 9 times a minus 1 equal to 0. And from here we can say that having a equal to 9 or a equal to 1, we will have a2 minus 10a plus 9 equal to 0. And since here we deal only with 3 cases, having, so in first case a is equal to 10, in second case a is equal to 9, and in the third case a is equal to 8. And we can see that for the second case, a equal to 9, we have this term equal to 0. And as a result, S1 and 2 is equal to minus 3 plus a, which is 9, over 4. So it's minus 12 over 4, or minus 3. So for the second case, s equal to minus 3 is a break-in or breakaway point. And we already have s equal to 0 as another break-in or breakaway point. So maybe I can just summarize it here. A equal to 10. We will have s equal to 0. I just call it S1. S2 equal to minus 3. S3 equal to minus 3. These are the break-in or breakaway points. Break-in or break away. Let's see what do we have. Sorry, this is with a equal to 9. The second case. Let's see what do we have with a equal to 10. If we set a equal to 10, what we have here, we will have, so 100 minus 100, 0 plus 9, which is a positive number, yeah? We will have a squared minus 10a plus 9 bigger than 0. As a result, here we will have square root of 9. Indeed, I can rewrite it. S1 and 2 will be equal to minus 3 plus 10 over 4 plus minus square root of 9 over 4 for a equal to 10. And from here we have minus 13 over 4 plus minus 3 over 4 for S1 and 2, or we can write S1 is equal to minus 13 over 4 minus 3 over 4. S2 is equal to minus 13 over 4 plus 3 over 4. This will give us minus 16 over 4 or minus 4, and this will give us minus 10 over 4 or minus 2.5. So these 2 points are the break-in or breakaway point for A equal to 10. So in this, I go back here. For A equal to 10, we have S1 equal to 0, S2 equal to minus 4, and S3 equal to minus 2.5 as the break-in or breakaway points. And for A equal to 8, for the third case, having A squared minus 10A plus 9, we will have a negative value here. Yeah? So in this case, A squared minus 10A plus 9 will be equal to 64 minus 80 plus 9, smaller than 0. Then we can say that this equation here, this polynomial here, doesn't have real roots. And therefore, we say that for A equal to 8, we have only one break-in or breakaway point, which is S1 equal to 0. So in other words, this is our initial conclusion about the break-in or breakaway points. Now what we need to determine is to see whether each one of these points belongs to the negative locus or positive locus, and whether they are a break-in or breakaway points. So let's go back to the previous step. This is what we have from the previous step regarding the real axis in the negative locus or positive locus. For the first case, for A equal to 9, we see that S1 equal to 0 belongs to the negative locus. This is in negative locus. So it's here between minus 1 and plus infinity. S2 equal to minus 3 is in positive locus, because it lies here between minus 9 and minus 1. And S3 is the same. So we have two break-in or breakaway points for the positive locus and one break-in or breakaway point for the negative locus. For the second case, S1 equal to 0 is in negative locus again. S2 and S3 are both of them are in the positive locus, because they are between minus A and minus 1. And for the third case, S1 equal to 0 is in the negative locus again. Okay, so I think now we can little by little start to draw the root locus. One more thing that we need to determine, I think, is the angle of departures from the pose at the origin. And then I think we will be done here. So, but before going to that, let me just start to draw the root locuses for three cases: A equal to 10, positive locus, negative locus, A equal to 9, positive locus, negative locus, A equal to 8, positive locus, and negative locus. For A equal to 8, we have two poles at the origin, two poles here, 1, 0 at minus 1, and the pole at minus 10. So two poles at origin, 1, 0 at minus 1, and one pole at minus 10. For a equal to 10, let's see what do we have in terms of the asymptotes. So it's the same for all of them, but xa is equal to 1 minus a over 2. So we will have three cases. A equal to 10, a second case a equal to 9, and third case a equal to 8. And in each one, xa will be different. A equal to 10, we will have minus 4.5 for xa. A equal to 9, xa will be equal to minus 4, and a equal to 8, xa will be equal to minus 3.5. And in all cases, the angles of the asymptotes are the same: pi over 2, 3 pi over 2 for positive locus, 0 and pi for the negative locus. So let's draw them for each case. A equal to 10, xa is at minus 4.5. So here is minus 4.5. Minus 4.5. We have pi over 2 and 3 pi over 2 for the positive locus, and pi and 0 for the negative locus as the asymptotes. For a equal to 9, we have two poles at the origin, one pole at minus 1, one pole at minus 9, and the same here for the negative locus. And in this case, xa is minus 4, minus 4 here, and the angle of the asymptotes are the same. So pi over 2 minus pi over 2, 0 and pi. And for the third case, we have two poles at the origin again, one 0 at minus 1, one pole at minus 8, same here. And this time the xa is at minus 3.5, and the angles of the asymptotes are again the same. So here we have pi and 0. Let's check the parts of the real axis which belongs to the root locuses. And we have them here. So from the area between minus a and minus 1 belongs to the positive locus, and the rest belongs to the negative locus. Between minus a and minus 1 belongs to the positive locus, and the rest belongs to the negative locus. So here for the positive locus between minus 9 and minus 1, for the negative locus the rest, and the same thing here for the other values of a. Now we can also determine the break-in, break-away points that we have here. We have concluded them here. So we can see that for positive locus a equal to 10, we have minus 4 and minus 2.5 as break-in or break-away points for the positive locus. So let's go and determine them here. So we had minus, again, just to be sure, we have them at minus 4 and minus 2.5. So minus 4 minus 2.5 are here. Minus 4 could be this point, and minus 2.5 could be this point. So you can just, yeah, this is minus 2.5, and this is minus 4. So those points belongs to the positive locus, the break-in or breakaway points. And then we have s equal to 0, which belongs to the negative locus. So this is another point right at the origin, which belongs to the negative locus. So this is a break in or break away point. So it is either break in or break away, and we can refer to the second derivative of rho with respect to s. But here we can see that since we have two poles at the origin, this point is for sure a break away point. So it's not a break in, but it's a break away point. In the case of positive locus, this could be a break in or break away point, either one of them, the one at -4 and the one at -2.5, and we will investigate it later. For a equal to 9, we have these three cases: S1 equal to 0 and S2 and 3 equal to -3 in the positive locus. So we have for a equal to 9, we have 2 points here, to break in or break away points at -3. And the point at the break in break away point at 0, which here we are for sure, we for sure know that it's a break away point. And for the last case, in which a is equal to 8, we have only one break in or break away point at the origin, which belongs to the negative locus. And again, we know that this is a break away point. And there's no break in or break away points for the positive locus. So I think the last thing that we may need to determine for some of cases is the angles of departure. Angles of departure from the pose. Let's see for which case do we need them. So here for a equal to 10, in the case of negative locus, we can see that we have one pole here, and this pole will move towards -infinity because this part of the real axis belongs to the negative locus. So I can say that we will have one branch here moving towards -infinity, starting from the pole here. And then since we have two poles at the origin, one of them will move towards the 0, and the other one will move towards the plus infinity using the asymptote on the real axis. So we are done with this case. Yeah, no need to find out the angles of departure from the poles. In any case, we will end up having pi and 0 for the angles of departure here. For the negative locus a equal to 9, we have similar case. So we will have one branch here going towards -infinity, one branch will go towards 0, and the third branch will go towards plus infinity. And it's the same for the last case. So we can see that the negative locus for all three cases are somehow similar to each other. Just the location of the third pole at -8, -9, or -10 differs from each other. Let's see what's the angle of departure for the positive locus from the poles at the origin. So we know that we have q times alpha departure equal to sum of phi I minus sum of theta I plus 2h plus 1 times pi for the positive locus. We can indeed calculate it for the negative locus, but as you already have seen, we don't need indeed. We are already done with that. Yeah. Since we want to obtain the angle of departure for the poles at the origin, for which we have 0 at -a and one pole at -1 and one pole at -a, and we need to put the test point here to find out the angle of angle phi 1 coming from the 0. We connect the 0 to that test point, and then we draw a line from the 0 towards plus infinity, and we can see that this angle is equal to 0 degrees. And the angle coming from the third pole as well, this angle is equal to 0 degrees. So q times alpha departure, therefore, will be equal to sum of phi I is 0 minus sum of theta I is 0 plus 2h plus 1 pi for positive locus and 2h pi for the negative locus. And since we have two poles here, h will be equal to 0 and 1, and q is equal to 2. So 2 alpha departure is equal to pi 3 pi for positive locus, 0 2 pi for the negative locus. Or in other words, alpha departure is equal to pi over 2, 3 pi over 2 for the positive locus, 0 and pi for the negative locus. So this is what we already have done. Yeah, we already have discussed it. And now for the positive locus, the angle of departures are obtained as pi over 2 and 3 pi over 2 for all cases. So it doesn't depend on the value of the a. Therefore, for all cases, we will have the poles departing with these angles, with 3 pi over 2 and pi over 2, as we have here. For this, indeed, for the poles at the origin, and for the third pole, since this part of real axis belongs to the root locus, we can calculate the angle of departure, but indeed we will have the angle of departure equal to 0 if you calculate it. So the branch at this pole will start to move towards the 0 at -1. Now we need to finalize our graph. For the case of a equal to 8, we see that there is no break-in or breakaway point. Therefore, this branch will continue moving towards the 0 at -1, and these branches will go towards infinity using the asymptotes. So we will have this kind of behavior, something similar to this. In the case of a equal to 9, we have a point at -2, at -3, which has occurred 2 times. And therefore, we can say that this point will be both a break-in and break-away point. So therefore, our branches starting from the origin, they will come towards s equal to -3. They will enter the real axis. And we will have a third pole, third branch coming from the pole at -9. They will meet here. Then one of the branches will go towards the 0. And the two will start to go towards infinity using the asymptotes that we already have drawn. So this will be what we have for the second case, a equal to 9, for the positive locus. And now for the last case, a equal to 10, we have two distinct break-in or breakaway points, one at -4 and one at -2.5. So one of these points will be a break-in point because the branches which departed the real axis at the origin, they will go at some point towards the real axis, and the other one will be a breakaway point because then the branches will depart the real axis and they will move towards the infinity using the asymptote that we have here. So this is our asymptote, which is already drawn. So which one is a break-in or breakaway point? One way is to refer to the second derivative of rho with respect to s and evaluate it at s equal to -2.5 and s equal to -4, and then determine the sign of the expression, whether it's bigger than 0 or smaller than 0. However, I may let you try this Just find out the second derivative of rho with respect to s by setting a equal to 10 and determine the sign. But here I can say that this the first point at minus 2.5 will be a break-in point, and the one at minus 4 will be a breakaway point. So the branches starting from origin, they will enter into the real axis here. One of them will continue towards the 0 at minus 1. One of them will go towards the breakaway point at minus 4. Another branch will come from the pole at minus 1 and it will arrive here. And then they will depart and go towards infinity using the asymptotes that we already have drawn. So this will be the case. And I will let you try this. If you cannot figure it out, how to know the point at minus 2.5 is a break-in and the one at minus 4 is a breakaway, just let me know and I can explain you in a very short video. So that's all. We end up with these root locus plots that we have for different values of a, both for the positive locus and negative locus. And you can see that depending on the location of the third pole, we have quite different results. Yeah, here we have a equal to 10, in which we had one breakaway and one break-in point close to each other here. This is for a equal to 9, and here we don't have any break-in or breakaway point rather than the one at the origin. And you see that the behavior, especially around minus 4 on the real axis, is quite different. I can also show you how the result looks like in MATLAB. So here we have G1, G2, and G3 as 3 different transfer functions. And with our locus of G1, G2, and G3, we can plot all of them in the same figure. And this is what you can see. Yeah. So for the blue line here, we have a equal to 10. For the green one, a is equal to 9. And for the red one, a is equal to 8. And you can see that here we have the green one having break-in and breakaway point at the same point, which is minus 3. So it's similar to what we have obtained. The blue one is the one in which we have 2 different break-in and breakaway points. And the red one is the one in which we don't have any breakaway point except the one in the 0 or in the origin. Okay, so that's all for this video. I hope you have enjoyed it and have learned how to draw the root locus, and you also have understood that the location of the poles would change sometimes may change the behavior of the root locus quite strongly. Yeah. All right. So thank you for watching, and see you next time.